All right, chapter 4, solving quadratic equations. This title should actually ring some bells for what we did in chapter 3. Chapter 3's title was very similar. Chapter 3 dealt with graphing quadratic functions. So the difference there is that chapter 3 really focused on taking some quadratic equation and translating that into a visual graph. And the way we did that is we took that equation, whatever we were given, that quadratic equation, and we created an XY table, which we would plug in X values, see what it did within the equation. It spat out a Y corresponding coordinate point. We'd graph those points. We'd have the shape of our graph. That was the focus of chapter 3. Okay. In chapter 4, we're going to be focusing on this right here. Solving equations. Solving equations should be something that you are more than familiar with when it comes to things that you've done just basically in general in algebra. A lot of algebra is based around solving equations. And so just kind of relating it to things that we've done semi-recently, solving equations has to do with anytime I'm basically trying to get X equals some value, Y equals some value. And we've done it recently with XY tables where I would take some given X value, something I chose, plug it into my equation to then solve for Y. Okay, we're going to be doing something similar here, but now we're actually going to be solving for X. And I'll show you what that means as far as like a visual difference in just a second. But I want to kind of break down, again, what this unit's going to be about. So we're going to be dealing with that solving, which means I'm going to be getting X equals or Y equals. And spoiler alert, we're going to be dealing mostly with X equals. So we'll be solving for X. The equation simply just means we're going to be dealing with the function end of the spectrum rather than the graphing end of the spectrum. We will have a section dedicated to interpreting a visual graph, but for the most part, most of this chapter is going to be based around like, all right, here is a given equation. Based on that equation, solve for X. Okay, so it's something you're familiar with. We're just going to deal with some new operations along the way. And part of that is going to be based on this term right here, the one that's familiar with chapter 3, quadratics. So quadratics, there's really a couple things we want to understand about that. First, visually, what we did in chapter 3, a quadratic is that U shape, also called a parabola. It's that a quadratic represents that curve. And we talked about happy face curves and sad face curves. Okay, that shape is called a quadratic, right? It's called a quadratic curve. Now that again is a reference to chapter 3, and visually that's what it looks like. But since we're dealing with equations here, what are we going to see in a quadratic equation form? Quadratics referred to x squared polynomials. Okay, so for instance, the standard form of a quadratic that we learned in chapter 3 was ax squared plus bx plus c. That's the general form of a quadratic equation. Now we'll see those different variations that we saw in chapter 3 as well. Those were all quadratics. They all had an x squared in some way, shape, or form. But that's what we're going to be dealing with in this chapter, solving those x squared polynomials for x, which may sound easy, but there are going to be some hoops that we need to jump through along the way. Okay, so that's the general purpose of the unit. The first section is going to deal with something that we're going to be needing to use. Properties of radicals. Properties of radicals. So properties of radicals, you may recall that we did a section on properties of exponents. Exponents. So exponents and radicals are actually inverses of each other. So this is the inverse of that previous section that we dealt with properties of exponents. I believe that was in chapter 2. So with exponents, that's the one that we typically are more familiar with. If I were to say, take some number like 5 and raise it to the power of 2, or square it, in other words, that would be telling me that exponent would tell me how many times that object is multiplied by itself. So if I were to take 5 and square it, raise it to the power of 2, that tells me I'm multiplying 5 times itself twice. So I'd have 5 times 5. My result would be 25. Okay, most of us are comfortable with our squares, and you'll notice that I have a squareds column here with our common squares. This will be worth writing down, and I'll reference this in just a few minutes. But again, back to that discussion. So for an exponent, it tells me how many times I multiply an object by itself. A radical, which is the namesake of our section, a A radical is the inverse of that. Basically, it undoes an exponent. So for instance, if I were to take 5 and raise it to the power of 2, I get the result of 25. If I wanted to undo that, I would take the square root of 25 to get back to the 5 that I began with. Okay, that root is another name for radical. This term radical is probably one that you're less familiar with, but the radical refers to this symbol right here. Okay, this is what we would call a radical expression, this root symbol that many of you are familiar with. There's a reason there's an n there. I'll talk about that in a second, but most of us are familiar with what's just called a square root, where I wouldn't even bother with the n. And I take the square root of a number. It's basically the answer to the question, what times itself twice gives me what's underneath that square root. For instance, the square root of 9. If I were to take the square root of 9, it answers the question, what times itself twice gives me 9? And the answer to that is 3. 3 times 3 is 9. So the square root of 9 is 3. It undoes 3 squared. Now, the reason why there's an n there, that n refers to what type of root, the nth root that I can take. In other words, we talked about this a little bit in a previous section when we dealt with some radical stuff and rational exponents and those sorts of things. But the n is going to refer to how many times I'm looking for the answer to multiply it by itself to get what's underneath. And that may have been a lot of words right now, I'm realizing. But the n, for instance, if this n was, say, a 3, that would be also calling this a third root, or a cube root, as some of you may know it. Okay, when I take the cube root or the third root of something, I'm basically asking what times itself 3 times will give me what's underneath that radical. For instance, the cube root of 27. Okay, and you'll notice a cube root, a cubed column right here. Again, worth writing down, and I'll talk about this in a minute. But this was one that we tend to have memorized less often, okay? But for something being cubed, it's times itself 3 times. So if I were to take the cube root of 27, I'm asking what times itself 3 times gives me 27? And the answer is 3. 3 times 3 times 3 gives me 27. The cube root of 27 basically undoes what is 3 cubed. Okay, and vice versa. So a radical is, again, if you want to throw this in the margin, a radical or root, either way is an appropriate way to call it. A radical or root basically undoes or is the inverse operation of an exponent. Okay, so one of the major things that you're going to be asked to do in this section is you're going to be asked to simplify radicals. Okay, and so this is a little process for what you're looking for, or at least some no-nos about what you don't want in your answer, about how to simplify a radical. And again, I'm going to go deeper into this tomorrow. This is mostly just an intro, but how do I go about simplifying a radical? Simplifying a radical, there are a couple things I want to look out for. This is similar to simplifying a fraction. Many of you have reduced fractions in the past and that sort of thing, and we're going to be doing something similar here, but now we're dealing with different math properties. And so with the radical, the first thing I want to check for are perfect n powers. That's a very fancy way, a very mathematical way of saying I'm looking for combinations of these numbers under those roots. Okay? Because basically, if I had something that said like, all right, simplify the square root of 16. Well, I can simplify that by just simply taking the square root of 16. The square root of 16 is an actual number. And that would be 4. 4 times itself twice would give me 16, right? So square root of 16 can be reduced or simplified down to simply 4. Now we're going to find a little more complicated versions of that as we get into examples tomorrow. There are ways that I can have leftovers, kind of like when I reduce a fraction, I can have leftovers and those sorts of things, or dividing, I can have leftovers. But I can't have perfect squares or cubes under a cube root left over underneath. Next thing is I can't take a square root of a fraction. So for instance, I couldn't have like some fraction like 3/5. I couldn't say like, all right, the square root of 3/5, right? The whole fraction, right? There is a way to break that apart into pieces, and we'll explore that in examples as well. All right. And then lastly, I can't have a radical or a root in the denominator of a fraction. It's similar to the last one, but this one now it's only in the denominator spot. So for instance, I couldn't have 3 over the radical or the root of 5. All right. And so there are ways to rearrange that. These are basically going to be stipulations for how I go about simplifying a radical. We're going to explore those more tomorrow. But before I end this, I want to talk about this stuff here in the margin. So you will notice 2 different columns being x squareds and x cubeds. These are the common ones, the whole number ones. And they're not obviously all of the squareds and all of the cubes. These are just the positive counting numbers up to 12. But these are valuable to have. Many of us tend to have this column memorized. Okay, for whatever reason, multiplication tables, whatever it may be. You probably have most of these memorized under your belt somewhere, right? You know, for whatever reason, you know that 8 squared is 64, or you know that 6 squared is 36. Okay. Now the reason why I put this in the margin, the reason why I suggest that you put this in the margin, isn't so that you know how to do it quickly. It's because we're going to be asked to identify these numbers very often throughout the section. And I was very good at this stuff when I was in high school, but having these things written down in my columns, in my margins and stuff, came in really handy when it came to, I want to solve problems quickly. Because it can be a pain to try and just on a calculator be like, all right, does this number squared give me that number? No. Okay, what about this number? Okay, there it is. That's time consuming, right? And particularly when it comes to like some of these other ones, these oddball ones, like 11 squared being 121. For whatever reason, that just tends to be something that we don't have memorized, right? But still, it's worthy to have these kinds of numbers in your margins, because you will come across this stuff in the examples. You'll see more in depth tomorrow. And the same thing goes for cubes. For whatever reason, we tend not to have these ones memorized, maybe a couple of them. I'll talk about some of the unique ones in tomorrow's lecture and stuff. But again, having these things written down will come in handy, because we're going to be looking for combinations of these numbers in our solutions. And just for the record, these cubes is not something we're going to be exploring throughout the rest of this chapter, because we're dealing just with quadratics, which is just going to be x squared. But this is mostly just going to be a practice in these properties of radicals as a way to illustrate what's going on. But we'll explore more of this stuff in depth tomorrow with actual examples from the section notes. But other than that, that will be about it. So let me go ahead and stop recording.